In this video, we're going to go over 3 different types of organic reactions: combustion reactions, addition reactions, and elimination reactions. So for combustion reactions, this has been a topic covered in Science 10 as well as Chemistry 20 here. Essentially what's happening is you have some sort of hydrocarbon reacting with oxygen, and your products are always going to be carbon dioxide and water vapor when you are talking about complete hydrocarbon combustion. If you're talking about incomplete hydrocarbon combustion, your products are going to be carbon monoxide, carbon, and water vapor. Okay, so because this is a topic that has been covered in previous classes, you are expected to be able to identify what combustion reactions are and also be able to balance it and predict the products. Okay, so again, just keep in mind combustion reactions, you'll have some sort of hydrocarbon and it's always reacting with oxygen. Okay, complete combustion will always give you carbon dioxide and water. Incomplete will give you carbon monoxide, water vapor, and carbon. Okay, so just keep in mind this little note over here before we move on. Even if there is a double bond in your hydrocarbon, you're still going to, like if you have a hydrocarbon reacting with oxygen, that is your key signal that you have a combustion reaction. Okay, so even if there's a double bond in your hydrocarbon, if it's reacting with oxygen, it's a combustion reaction, not necessarily addition reaction. Okay. The reason why I mention that is just because in the next section with addition reactions, essentially what you're looking for is you're looking for a double or a triple bond, and that's going to be your location to add whatever other reagent you have. Okay, so atoms are added to a carbon-to-carbon double or triple bond. A variety of molecules can be added to a double or triple bond. But usually the ones we see are going to be water, hydrogen. HX just means hydrogen with some sort of halogen, so fluorine, bromine, iodine, chlorine, something like that. X2 just means some halogen, so fluorine, bromine, iodine, so on and so forth. Okay, so the key part to being able to identify when something is an addition reaction is one of your reactants is going to be a hydrocarbon with a double or triple bond, and the same 2 carbon atoms are bonded to 2 new atoms in the product. Okay, so as our example here, we have some hydrocarbon with a double bond in it, and the other reactant is this imaginary substance where Y is bonded to Z. Okay, and essentially just what happens is like one atom in the second reagent gets added to one side of the double bond and the other atom gets added to the other side of the double bond in your hydrocarbon. Okay, and as they get added, this double bond turns into a single bond. Okay, so that's the key idea behind an addition reaction. You have your double bond, you're adding 2 atoms or more. It just kind of depends if you're working with a double or triple bond. Okay, so essentially you're adding atoms to either a double or a triple bond, and one of the atoms is going to be added to one side of the double or triple bond, and the other atom is going to be added to the other side, and then you're going to reduce your bond by 1. So in this case, we're going from double to single. Okay, so you'll see this explored in our examples here. Okay, so for example, we have some double bond or some hydrocarbon with a double bond in it. If we're adding hydrogen to it, we're just going to get an alkane. Okay, so one of these hydrogens is being added to one side of the double bond, and then the other hydrogen is being added to the other side, and then our double bond here becomes a single bond, okay? And the same situation is going to happen over and over again. Okay, so if we're adding water to a hydrocarbon with a double bond, okay, hydrogen gets added to one side of the double bond, and the OH group, or the alcohol group, or also known as the hydroxyl group, gets added to the other side. So keep in mind, you could get this as a product, or you could get this as a product. Okay, so could go either way. Okay, the main idea is that you're able to predict at least one possible product when there's no, like in Chem 30, we don't go into far enough into the rules to be able to make a more accurate prediction as to which one of the products will be more favored in the reaction. Okay, so when we're adding hydrogen attached to some halogen, again, one gets attached to one side of the double bond, the other gets attached to the other side, and then we're left with a single carbon-carbon bond. Okay, alternatively, you could also get this. Okay, and then last but not least, we're just adding a halogen to our hydrocarbon that has a double bond in it, and then for this, because both of these atoms are the same identity, this is going to be the only product that you get. And again, main idea is the atoms are added to either side of the double bond, and then the double bond becomes a single bond. Okay, so first example here. Chlorine gas is involved in an addition reaction with butene. Okay, so first off, let's just draw butene. So but means that there's 4 carbons in the parent chain. Ene means there's a double bond on carbon 2. So I'm going to draw this out. 1, 2, 3, 4, and then double bond starting on carbon 2. So I'm counting my carbons like that. Okay. So now we're adding in chlorine. So chlorine is one of our diatomic elements. So how you can remember your diatomic elements, I just like to abbreviate it to Hofbrinkel. Okay, so this is your list of all diatomic elements, so that means whenever they're by themselves, there's always 2 of them, okay, or 2 atoms of them. So your diatomic elements are hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Okay, so I'm gonna draw chlorine just like so. Okay. And then we're just adding the chlorine to either side of this double bond. So what that's going to look like, 1, 2, 3, 4. Actually, I'm going to draw that a bit better. There we go. And then here's our chlorines. And then our double bond becomes a single bond because we added in the chlorines using this second bond there. Okay, and then that's done. For example 2, we have excess chlorine is added to ethyne. Okay, so I'm going to read the note first before I draw out how this happens. So if excess is added to an alkyne, so hydrocarbon with a triple bond, the triple bond will become a single bond as all atoms are added. If the amount of the added substance is limited, then a triple bond would become a double bond as only 2 atoms could be added. Okay, so basically what that's saying is make sure you pay attention to the words being used in the chemical reactions that you're given. Okay, so starting off with ethyne, so F just means there's 2 carbons in the parent chain, and then ine means there's a triple bond. So this is going to look like that. Okay. So with this, it's like the line drawing is a little bit hard to kind of wrap your brain around. So I'm going to instead just draw this as a structural formula. Okay. And then we're drawing chlorine again. So I'm going to kind of go over this slowly. So this isn't the final answer here. Okay, but let's just draw out our compound and I'll show you how we're adding here. Okay, so if we add 1 chlorine to this, that's going to take up one of these bonds. And so we're going to have chlorine added here and here. Now, if you instead drew the chlorine over here, that's totally fine. It's still the same compound. Okay, but notice how we still have extra bonds and excess chlorine is added. Okay, so based off of our note, we need to be making sure that the triple bond, when we have excess, becomes a single bond. So essentially, what that means for us, we got to keep on adding chlorines. Okay, so let's add another molecule of chlorine. Okay, so that's going to use up this bond, and we're adding the chlorine there. Okay, so now that our triple bond has become a single bond, now we are done. Okay. So that's the key note here that we should, I'm going to just take some time to write this out. So when I say when there's excess of a reagent, I'm not talking about the hydrocarbon, I'm talking about the other non-hydrocarbon reagent. Okay. So when an alkene or alkyne contains more than 2 carbon atoms, more than one product may form. The products are going to be isomers. Usually one isomer is more common than the other. Okay, so this is what I was talking about before. We can get isomers as products, but in Chem 30 we don't really go into a whole lot of detail that would give you the additional information needed to say which product is more common than the other. So as long as you draw one of the possible products, you're pretty much good for Chem 30. Okay, so let's look at example 3. So pent-2-ene is involved in an addition reaction with hydrogen chloride. So let's draw out pent-2-ene. So pent means 5 carbons in the parent chain, and there is a double bond on carbon 2. So 1, 2, 3, 4, 5. There we go. So I'm counting my carbons. like that. Okay, so we're adding hydrogen chloride. So I'm going to color code this so it's just easier to track where everything's going. Okay, so with this, one of our products, the hydrogen will be added, let's say, on the leftmost side of the double bond. Okay, so let's draw that out. 1, 2, 3, 4, 5. We have our hydrogen, and then we have our chlorine added to the other side. Okay? Or an isomer of our product could be if basically if the hydrogen had added to the other side instead. Okay? So 1, 2, 3, 4, 5. Hydrogen, and then chlorine. Okay, so these compounds here, they are isomers. Okay, and on a test, if you draw one of these, you are good. Okay. Now, there is something called Markovnikov's rule, which essentially tells you that where the hydrogen is most likely to attach. So here it says the hydrogen atom on the small molecule will attach to the carbon that's already attached to the most hydrogen atoms. Okay. Now, in our example that we just did, okay, if we look here at our two carbons that were involved in the addition reaction, both of them only had one hydrogen attached to them. So when hydrogen chloride was added, essentially it didn't matter which way hydrogen or which atom hydrogen attached to, like based off of Markovnikov's rule, is because neither of these carbons are more hydrogen rich than the other. Okay, so for the information that we have in Chem 30, both of these products are equally possible to get as a result from this reaction. Okay, in our next example, we have propene reacting with hydrogen chloride. So propene, that just means 3 carbons, 1, 2, 3, and then we have our double bond. Okay. Now, could we have drawn this like this? Yep, it's the exact same thing. Okay. So with this, I'm going to add my hydrogen chloride. Okay, so with what we have now, actually, you know what I'm going to do? I'm going to draw this, instead of a line diagram, I'm going to draw it as a structural diagram just so it's easier to see which carbon is more hydrogen rich. Actually, that one had the double bond to it. Okay, so we can see that this carbon has 2 hydrogens, whereas this carbon only has 1. Okay, so according to Markovnikov's rule, this hydrogen is going to add to this carbon because of the rule. The hydrogen atom on the small molecule will attach to the carbon that's already attached to the most hydrogens there. Okay, so when we're drawing our products, what that's going to look like So our hydrogen from our hydrogen chloride is right there, and then chloride goes right there. Okay, so that would be the most likely product according to Markovnikov's rule. Okay, so just keep in mind that Markovnikov's rule isn't really tested for in Chemistry 30, and ultimately you only need to be able to draw one of the possible products. All right. So what that means is if on a test you had this reaction, and if instead what you drew was, here, I'll change my color here. If what you drew instead was chlorine on the last carbon, then you would still be fine, okay? And the hydrogen attached to the middle carbon, you would still be fine, okay? But just so you know, according to Markovnikov, this is the most common product that you will get out of this reaction, okay? All right, so addition reactions and cyclic hydrocarbons. So with cycloalkanes, essentially if you add hydrogen to a cycloalkane, so that process is called hydrogenation. When you add hydrogen to a compound, basically what that's going to do is it's going to take your saturated cyclic hydrocarbon and it's going to break the ring. So you're going to go from a ring to a carbon chain. So for example, let's say we had cyclobutane, and since it's hydrogenation, we are adding hydrogen. Okay, so I write 2 atoms of hydrogen because hydrogen is part of Hofbrinkel, which is our diatomic elements. Maybe I'll add that in, diatomic elements. There you go. All right. So when we're taking cyclobutane, adding hydrogen to it, it's going to go from a cyclic compound to a chain. Okay, so we're still going to have 4 carbons. We didn't add any carbons, we're just adding hydrogen. So we go 1, 2, 3, 4. Okay, if you're wondering how on earth that works, okay, it might help you to look at the molecular formula for this. So the molecular formula for cyclobutane would be C4H8. Okay, and now if we look at the molecular formula for butane, it's going to be C4, and then let's count up the implied hydrogen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so essentially this is how you can kind of double check that you're drawing the right product here, is you can go, okay, my first compound, or my cyclic compound that I started off with was this. I added 2 atoms of hydrogen. Does this molecular formula make sense for my product? Yep. Then we move on. Okay. Let's just get rid of these. Okay, for cycloalkenes, so that's a cyclic compound with a double bond in it. Okay, addition reactions, they're going to cause the alkene to become saturated. Okay, so essentially the addition reaction is going to use up that double bond and turn it into a single bond. So for example, let's say we had this. So that'd be cyclohexene, and let's say we are adding bromine. Essentially what would happen is bromine would be added to either side of this double bond. and then the double bond would be turned into a single bond because it gets used up taking on that bromine. Okay. So again, what's expected of you to be able to know is you're expected to be able to predict products and write and interpret balanced equations for simple addition, substitution, elimination, esterification, and combustion reactions. So we've done combustion reactions and we just did addition reactions, and we're going to move on to elimination reactions. So actually, let's highlight this, because that's important for you to be able to know. Okay, so elimination reactions, what they are is essentially the opposite of an addition reaction. So two atoms are removed from your organic molecule and a multiple bond forms. So what that means is either a double or a triple bond is going to form. Okay, so either a double or triple carbon-carbon bond. Okay, so one way in which you can recognize it, if you're just looking at a reaction that has the reactants as well as the products, is the carbon atoms in the organic product are bonded to fewer atoms in the organic reactant. Okay, so here we kind of have a template of how this happens. So we have some hydrocarbon that has a single bond between two carbon atoms, and as these two atoms are removed from the compound, okay, so they go off and form their own compound, and as a result, the single bond between those two carbons turns into a double bond. Okay, so for Chem 30, you don't have to get into the mechanics of exactly how that happens. You just have to be able to predict what your products are going to be. Okay, but in terms of the mechanics of how this happens, that's something that'll be covered in university. Okay, so alcohols can undergo elimination reactions to produce an alkene and water. A strong acid is needed for the catalyst to speed up the reaction. Okay, so let's do an example of an alcohol in an elimination reaction. So we're given propane 2-ol, so prop means that there's 3 carbons in our parent chain, 1, 2, 3, and then 2-ol means that there's a alcohol group on the second carbon. Okay. So because we need a strong acid as a catalyst, I'm just going to write strong acid over top of the reaction arrow, because that's typically, if you had a catalyst, that's typically where they'd go. Okay. All right. So essentially what's happening here, okay, is this alcohol group is going to basically leave this hydrocarbon, but it's going to take another hydrogen from this compound with it. So it could be this hydrogen, or it could be this hydrogen. Okay, so it has to be a hydrogen on a neighboring carbon. So it's going to look like we get 3 different products. However, 2 of them are the same. They just look a little bit different from each other. Okay, so what we're getting, so let's say we have water, okay, and for the hydrocarbon, what that's going to look like is it can either look like this, okay, so it'll look like this if this leaves with this, okay, but you could also write your product as that, assuming this alcohol group leaves with this hydrogen. However, one thing about this that you need to know is that both of these are the same compound, okay? Both of these are, you could call them propene or prop-1-ene. So same compound. So you don't need to draw both, just one. All right. Example number 2, draw the structures for pentan 2-ol in an elimination reaction. Yes, more than one structure can form. Okay. So pent means that there's 5 carbons, there's an alcohol group on carbon 2. So 1, 2, 3, 4, 5. And there's my alcohol group on carbon 2. We have our strong acid as our catalyst. All right, and now I'm just going to highlight the hydrogens so it's easy to see kind of what I'm talking about here. Okay, so I'm going to highlight this hydrogen and this hydrogen. Okay, so let's say for our first product, actually for our first product, I'm just going to get water out of the way because we know that's leaving this compound. Okay, now for our next product, I'm going to say this alcohol group is leaving and taking this hydrogen with it. So the product that we're going to get is going to be 1, 2, 3, 4, 5, and the double bond will be here. Okay, so the double bond occurs in the 2 carbons kind of between this alcohol group and this hydrogen. Okay. But the other product we could get could happen if this alcohol group left with this hydrogen, and in this case, yes, you are going to get 2 different compounds. Okay, so 1, 2, 3, 4, 5. So if these 2 leave, then that means the double bond forms here in between those leaving groups. Okay, so this product, that's going to be called pentene or pent1ene. Whereas this product is going to be called pent2ene. Okay, so as you can see, you do get 2 different products. They are isomers of each other. But for the purposes of Chem 30, as long as you're able to draw one of these, you're good. Okay, so we get 2 different hydrocarbon products, okay, which are isomers. Okay, and of course we get water as well. Okay, so when I say 2 different products, I mean 2 different hydrocarbon products. Maybe I should throw that in there. Okay, but the key idea for elimination reactions, when you have an alcohol undergoing an elimination reaction, what you're going to produce is water and some sort of alkene. Okay, so just watch out. Don't forget to write water as one of your products, because that is very easy for students to forget. Okay, so isomers can form from elimination reactions also, like we just saw over here. You don't need to be able to predict which one would be most common, but you do need to be able to draw at least one of the possible structures.